class, welcome to our guided notes section on skills 10 and 11. In this video, we will be focusing only on part 1 of this outline, and we will finish this outline in a second video. For the first part of this note outline, I want to first connect the concept of a rational exponent to prior knowledge, and for that, I'm going to transition over to a PowerPoint that will walk us through one example using addition and then another example using multiplication, so you can kind of see the similarity between the two. So let's transition there now. So on the addition side, I want you to first consider what it means to add the same number over and over again. Like if I were to add a bunch of threes together. So here I've got 1, 2, 3, 4, 5, 6, 7, 8. 8 threes. So is there a shorter way to write 3 added to itself 8 times? Question mark. The answer is yes. We use multiplication, right? Multiplication is a way for us to sort of shorthand or abbreviate what it means to add the same number to itself over and over. So 3 times 8, or you can switch it 8 times 3, because multiplication is commutative, is 24. So 8 threes basically added together is 24. So repeated addition is basically multiplication, and this 8 is just telling us how many threes we had added together. So it's the sum of 8 values of 3, basically. Okay, so then let's think about what repeated multiplication could be written as, right? If I want to multiply the same number over and over again. So this is again 1, 2, 3, 4, 5, 6, 7, 8 threes. This time these 8 threes are being multiplied together versus added. So is there a shorter way to write that? And the answer is yes, right? That's what exponents do. They help us keep track of how many times we're multiplying the same number to itself. So here it's basically saying this is the product of 8, right? 8 factors of 3 multiplied together equal this number right here, 6,561. Okay, so keeping all that in mind, when we think about multiplication, that's repeated addition. So then division would kind of be doing the reverse, right? 1 over 8, dividing 24 by 8. So what is the meaning of 1/8 of 24? Well, it would be 1 of the 8 numbers that add up to equal 24, right? 1 of the 8 parts, the 8 values that add to 24, which is 3, right? 24 divided by 8, split into 8 equal parts would be, and 1, this is 1 of those 8s would be 3. 1 out of the 8 values that add to 24. Okay? That's a fraction when we're thinking of it in terms of division, right? 1/8 of 24 is like 24 divided by 8. So it's just talking about 1 of these 8 values that add to 24. So that's 3, right? 1 of the 8 values that add to 24 is 3. Similarly, when we start thinking about fractions in the exponent spot, it has a similar idea. Is now we're like, okay, we know that 3 to the 8th power is 3 times itself 8 times. So if I want to take a 1/8 power, it has a similar meaning. It means 1 of the 8 factors. So now it's not values that are adding, it's factors that are multiplying. So 6,561 to the power of 1 over 8, which is the division in the exponent area, is doing something similar. It's saying, I want to know what 1 of the 8 factors that multiply to 6,561 equals. And that would be 3, because we know that 3 times itself 8 times is 6,561. So therefore, 1/8 of, or 6,561 to the power of 1/8 would mean 1 of the 8 factors that multiply to 6,651, which is 3. 1 out of the 8 numbers that when you multiply it to itself over and over again gives you 6,561, and that number is 3. Now, what if the numerator doesn't equal 1? So suppose instead of asking for 1/8 of 24, now we want to know what 5/8 of 24 is. It's simple. Instead of just taking 1 of the 8 numbers that add to 24, we take 5 of the 8 numbers that add to 24, right? 5/8. So 5/8 of 24 would be 5 threes added together. 3 plus 3 plus 3 plus 3, 5 times. Because 3 added to itself 8 times is 24, and I want 5 of those. So I add it to itself 5 times, and then I get 15. Similarly, if you have an exponent like that, right, a fraction where the numerator isn't 1, we can think of it in the same way. So before it was 1 of the 8 factors that multiply to 6,561. Now it's 5 of the 8 factors that multiply to 6,561. So that would be 3 times itself 5 times, which equals 243. Because 1/8, right, 1 of the 8 factors that multiply to 6,561 is 3. But this is asking for 5/8. So I take that 1/8, 3, multiply it to itself 5 times, and get 243. So let's see if you got it. Try these. So the first one is 3, because I'm looking for one of the 2 factors that multiply to equal 9. 3 times 3 is 9, so one of those factors is just 3. Number 2 is 2, because this is asking for one of the 4 factors that multiply to 16. And so that would be 2, because 2 times itself 4 times. 2 times 2 times 2 times 2 is 16. So if you had to think of a number that multiplies to itself 4 times to get 16, that would be 2. And this is asking for 1 out of those 4 factors. So only one of them is 2. So you might be going, this was like finding a square root. It was finding what's one of the numbers that when you multiply it to itself twice equals 9. That's a square root. This is like a 4th root, because we were having to find one number that when I multiplied to itself 4 times equals 16. And that number was 2. And you would be right. You'll have to see momentarily. You will be right. Now this last one is a little trickier because the numerator wasn't 1. The numerator was 2. But we still had to think about what number times itself 3 times gives us 27. So we had to think about the cube root of 27, right? What number times itself 3 times equals 27? Well, that number is 3, right? 3 times 3 times 3 is 27. But the numerator was 2. So it was saying, give me 2 out of those 3 factors. Give me 2/3, basically, right? 2 out of those 3 factors would be 9, because 9 would be 3 times 3, twice. Okay, so let's head to our outline. So there's 2 key concepts covered in that PowerPoint. And the first one is the idea that a rational exponent is none other than just a root. An nth, a 1 over n power is basically the same thing as an nth root. Here I have an example, 8 to the 1/3 power. So according to the video, we would think about, okay, what number has to multiply to itself 3 times to equal 8? And then the fact that it's 1/3 means we just take one of those 3 factors, which is 2. But that's basically just a cube root of 8, basically. So a 1 over 3 power is just a cube root of 8. And then when the numerator is something other than 1, so now we have like an m over n fraction, we can think of that in 2 different ways. First, we could think of it as taking the nth root first and then raising that to the power of m. Or we can think of that as raising it to the power of m first and then taking the nth root. This is the way that I find to be the easiest to do. And I have an example here. So when I have something like 27 to the 2/3, where we just looked at that one in the PowerPoint, first we have to think about like what number times itself 3 times is 27, right? What 3 factors are we thinking about here? And that number is 3. But then the numerator is 2. So then we have to say, okay, well, I need 2 of those 3 factors that multiply to 27. So then that means I need 3 times 3, which equals 9. Right? So really what we did is we took the cube root first. We had to figure out what number times itself 3 times is 27. So that was the cube root of 27, which was 3. And then we took 2 of those cube roots. So we squared it essentially, right? We took 2 of those factors. When you take 2 of the same factor and multiply them, you're squaring that thing. And so that's how we got 9. So that's basically how rational exponents work. These are the 2 main things you have to remember. The denominator in the rational exponent is the same as the index or the root, right? And the numerator is the same as the exponent. So it's telling you how many times to multiply that number to itself. And another thing is that the rational exponents will follow all of the existing rules of exponents. So that was in your Khan Academy review from Monday. And here's just a little table of them to reference when you're doing your homework or even going through this video. This is just sort of a quick summary of what all of those rules are. And I just realized I forgot to state an example for this. This is just basically saying that if you have two things that are being divided, maybe like 2/3 or something, and you raise them to a common power, let's say I'm going to raise it to the 4th power, you basically distribute the power. This is the same thing as 2 to the 4th power divided by 3 to the 4th power. You just raise both the numerator and denominator to the same power. So that would be 16/81. There's our example for division. The main thing you need to also remember when working with exponents is that you cannot distribute an exponent over addition or subtraction. So this is what not to do, right? A plus b to the power of m does not equal a to the m plus b to the m. Similar for subtraction. A minus b to the m does not equal a to the m minus b to the m. All of these things would require foiling, right? When you have a binomial to a power, you have to FOIL it. But you can distribute an exponent over multiplication, right? Here in this property, you can distribute the power of n to both x and y, and you can distribute it over division, just not addition or subtraction. So those are the main things to remember. And now we're going to just walk through all the different question types that involve rational exponents. This video, we're going to walk through the first 2, and then the second video, we'll walk through the remaining 3. So let's look at question type number 1. Question type number 1 is when we are evaluating. So the thing to remember about evaluating is we're looking for a number answer, an answer that's a value, not so much an expression. So 64 to the power of 1/3, that means I need one of the 3 factors that multiply to equal 64. So I have to think to myself, what is the cube root of 64, right? What number times itself 3 times will equal 64? And that number is 4, right? 4 times 4 times 4 is 64. And this wants to know what one of those 3 factors is, right? 64 to the power of 1/3 would be one of the 3 factors that multiply to 64. So this answer would just be 4. Or you can just think of that as the cube root of 64. In example 2, I've got 8 to the power of 2/3. So first I have to kind of think about what number times itself 3 times is equal to 8. So that would be 2 times 2 times 2. And since the numerator is a 2, then I need 2 of the 3 factors that multiply to equal 8. 2 of the 3 factors that multiply to equal 8. That's really what that means. And so the answer would be 4, right? 2 times 2 is 4. The other way to think about that is using the key concept number 2, right? B to the m over n is equal to the nth root of b raised to the power of n. So I could think of this as the cube root of 8, because the denominator is the index, and that's 2, right? The cube root of 8 is 2. The number that multiplies to itself 3 times to equal 8 is 2. And then I take that cube root of 8 and square it, because the numerator of a rational exponent is the power. So the denominator is the index, so I do a cube root of 8 and get 2. The numerator is the power, so I take that 2 and raise it to the power of 2 and get 4. That's the other way you can think about it. One thing I also want to point out is that this answer is less than 8, as it should be. Because 8 to the 2/3, let me erase those, get those out of your way. 8 to the 2/3 should be less than 8 to the 3/3, right? And 3 over 3 is 1. That would also mean 3 of the 3 factors that multiply to equal 8. Well, all 3 of them, 2 times 2 times 2 equals 8. So 8 to the 1st is what that would equal. And this is 8 to the 2/3. So that should be less than. That should be a value that is less than 8. because 2/3 is a power that is less than 1. So I point this out only for you to be able to check the reasonableness of your answers. So when you have a number raised to a fraction less than 1, your final answer should be something less than the base. Moving on to example 3, we now are confronted with a negative rational exponent. But remember, rational exponents follow all the same rules as regular exponents. So this means to take the reciprocal. So this is equal to 1 over 49 to the power of positive 1/2. And the power of positive 1/2 means one of the two factors that multiply to equal 49, or 7. I'm going to write it this way too. You can think of it two ways. Or you can say, okay, the denominator is the index. So 49 to the power of 1 over 2 is just the same thing as the square root of 49, which is 7. And it's 1 over 7 because the exponent originally was negative, which means I need to take the reciprocal, and it ends up in the denominator. In the question or example 4, it's a similar thing where you have two bases that are the same that are being multiplied. So, and the exponents are rational, but they follow the same rules as normal exponents. And according to the rules of exponents, we need to add the powers. When the bases are multiplying, the powers add. So I would take, my answer to this would be 27 to the power of 1/3 plus 4/3. I would add them together, and that would become 27 to the power of 5/3. Now, before I evaluate this, I want us to think about the fact that this answer should end up being greater than 27 because the power of 5/3 is greater than the power of 1. But let's think about what 27 to the power of 5/3 equals. Well, that would be 5 of the 3 factors that multiply to 27. Well, the 3 factors that multiply to 27 are 3 times 3 times 3, right? That's the cube root of 27 is 3. And this is saying that we need 5 of those factors. So I would need 3 times 3 times 3 times 3 times 3. 5 of the 3 factors that multiply to equal 27. And that equals 243. So that's the way I like to think about it, right? But really what I'm doing is, I know the denominator is the index. So I'm finding a cube root of 27, right? That's what I was doing when I figured out what the 3 was. Cube root of 27 is 3. But then my numerator is 5, and my numerator is telling me how many times I have to multiply that root to itself. So I'm finding a cube root of 27. What number times itself 3 times is 27? That's a cube root. In this case was 3. And then I'm saying, okay, I need 5 of those. So I need to take that cube root of 27, which is 3, and raise it to the power of 5. Multiply it to itself 5 times to get to 43. So this process is using the key concept number 2 from earlier in your notes. And this concept is using the idea from our PowerPoint. So now we come to question type number 2, which is where we're basically converting from rational exponent form into radical form. And then we have to simplify those radicals at the end. So with example 5, we have y raised to the power of 4/3. So the denominator of 3 is going to be our index, and the power of 4 is, or the numerator of 4 is going to be the exponent. So when I write this using a radical, it'll have an index of 3. So that means it'll be a cube root. And the power of y under the radical will be 4. So y to the power of 4/3 is the same thing as the cube root of y to the 4th. So you could write it that way, or you could write it this way: the cube root of y separately, and then all of that raised to the 4th power. I will say that this is the way we write it for purposes of evaluating, right? This is the ideal way to understand a rational exponent when you're having to evaluate. But when you're simply converting from rational exponent into radical form, this tends to be the way we're most familiar with. And it's how we are used to seeing radicals when we have to simplify them. So that's why I chose to put the power of 4 underneath the radical. So from here, we can see since the power under the radical is more than 3, let me bring this down here. I can say that this is equal to the cube root of basically 4 factors of y, right? Because it's y to the 4th. And so I can see there's a perfect cube root in there, right? I've got 3 identical factors. That's a cube root of y. So I can pull one y out of the cube root sign. And then, of course, this remaining y will have to stay inside. So then the simplest answer, or the answer in simplest radical form, would be 1 perfect cube root of y on the outside times the cube root of y to the first power that was on the inside. So y to the power of 4/3 is equal to the cube root of y to the 4th, which is equal to 1 whole y to the first power times the 3rd root of y. Now in example 6, you can see we have 2 different bases. One is m, the other one is n, but they have matching indexes of 4. They're both raised to rational exponents with the same denominator, which is going to be the index. So these variables and powers are going to go underneath a 4th root sign. So it's the 4th root because both of the denominators are 4. And then the exponent for m will be 3, so it'll be m to the 3rd. And the exponent for n will be 5, n to the 5th. So this is using the first form of key concept number 2, where I just make the denominator the index and the numerator is the power of those bases under the radical sign, right? This is the typical way we write these when we're merely converting from rational exponents to radicals. Now the m to the 3rd is already in simplest form because there's only 3 factors, not enough to make a perfect 4th root. But we can see that the n can be simplified further since there's 5 of them. So we can think of this as the 4th root of m to the 3rd and then 5 factors of n, 4 of which make a perfect 4th root of n. So then I can take 1 whole n out. I have 1 whole root, 4th root of n. And then the m to the 3rd has to stay underneath the radical, and then this other 5th factor of n has to stay under as well. So it's n times the 4th root of m to the 3rd times n to the 1st. So that's our final answer for example 6. Lastly, with example 7, we want to convert this into a radical, right? We want this to equal the radical of something, but I need to figure out what my index is going to be because I do need to make them match. So because the index is determined off the denominator, I need to find a common denominator for these fractions. So right now I've got 2 and 3 and 6 in my denominator. So I can see that the lowest common denominator between all those 3 numbers would be 6. So for the 2 to the 1/2, I'll think of that as 2 to the 3/6, since 3 over 6 is equivalent to 1/2. For a to the 2/3, I'll think of that as a to the 4/6, because 4/6 is equivalent to 2/3. And then the last one can stay the same, b to the 5/6, because it already had a denominator of 6. So now I have the same fractions, but written with a common denominator of 6. So now I have a common index. So now I can put a 6 up here. I can say this is the 6th root of, but now look, my numerators are all different. Well, not all of them, but the first 2 are. But in order to get that common denominator of 6, I had to multiply the same number to the top and bottom, right, of the fractional exponent. So that changed my numerator. So now it's going to be 2 to the 3rd, not 2 to the 1st, times a to the 4th, not a squared, and then b to the 5th. That was the same as before. And then we'll just simplify that a little bit. So that's the 6th root of 8, a to the 4th, b to the 5th. And there is our final answer for number 7. So I will save question types 3, 4, and 5 for our part 2 video. And I'll see you there.